Okay, so just as a group could have subgroups, then a ring can have subrings. And a subset S of a ring R is called a subring of R if S itself is a ring with respect to the same operation that we had in R. And just as with groups, we had the one-step subgroup test. With subrings, we have theorem 12.3, which is a subring test. And that says that if we have a ring R and a subset S of R, then S is a subring of R if all of the following are true. Number 1, S is non-empty. Number 2, for all A and B in S, we have that A minus B is in S and A times B is an element in S. Okay, so let's talk about how we would prove this. So the first thing that we could think about is we need to show that if these two conditions are true, then we have an additive group, we have closure under multiplication, and we also have that multiplication is associative and distributive. So let's go through, and I listed those things basically over here on the right. So let's see if we can come up with an argument that that is true in an efficient way. So let's take any A and B in S. Okay, so we're gonna deal with the commutative group first, the commutative group under addition first. Well, we have the one-step subgroup test, right? And the one-step subgroup test says that if we have non-empty and we have that for AB in our subgroup, A minus B is in our subgroup, then we're good to go. And we have all these things. So we know it's non-empty because it's given by 1. S is non-empty. And by 2, we have A minus B is an element in S. And so by the one-step subgroup test, we know that S is a group under addition. So this shows that S is a group under addition by the one-step subgroup test. So let me check that off. So we've had no non-empty. We have we have group under addition. Do we have abelian? Well, yeah, we do have abelian because the abelian part is just inherited from our ring overall. So commutativity of addition is inherited from R. So commutativity is inherited from the big ring R. So we can check off a few more things. So we have our abelian group. Now closure under addition, that was just part of being our group under addition. So I actually listed that twice. So the only thing that we have left to deal with is multiplication is associative, and that's also inherited from our big group R. So, and then distributivity in our subring is going to be the same as distributivity in our big ring, so that is also inherited from our big ring R. So we can say that. So since S inherits multiplicative associativity and distributivity, from R. Really, the only thing that we need to deal with is closure under multiplication. But closure under multiplication, that is our condition number 2. So this is given by the second part of part 2 right there. And so we've dealt with multiplication is associative because it's inherited. Distributivity is there because it's inherited. And then we just said that we do have closure under multiplication because that is guaranteed in one of our hypotheses right there. And that's it. So if we can show these 3 things listed in our subring test, then we can show that a subset of a ring is indeed a subring. So again, we need to show that there's something in it. We need to show that for 2 elements, A and B in S, A minus B is in S, and we have to show that for AB, A times B is also in S. So these 3 things. And we're going to see an example of how to apply